And now let's start again, because this is the real thing, okay? Real thing as in, our course is called Data Structure and Algorithms. Now I'm going to introduce you the big O notation, which is going to be used in the subsequent 11 weeks and probably in your later computer science life to talk about uh, all this efficiency algorithm, okay? Are you ready? Let's start. Let me ask you, if I'm going to play a game with you, one person have a number from my heart, 1 to 100, and you have to guess my number. But I can, if you guess the number wrongly, I will tell you your number is too big or too small. How many times do you need to guess? Very good, Sanjay. 7 or about that, right? Or some people will say, oh, why don't I guess from number 1, number 2, number 3, number 4, surely win, right? Okay. 7, why you can do it in 7 times? Sanjay, can you suggest why can you guess in 7 times? I can guess the number. Yeah, binary search, right? Because the most clever way is I actually guess 50. And then you tell me it's bigger or smaller and then go, right? Very good. What if my number is from 1 to 1,000? How many times now? Yeah, very good. Sanjay say about 10. How about 10,000? About 14, maybe. How about n? If let's say today I'm going to say, oh, from 1 to 1 million or 1 to any number of n, how can you guess? How can you tell me what is the minimal number you need to guess? Yeah, sometimes log n base, right? So can you notice that what is the relationship with n and the number of time of to guess? You can say log base, right? They do not grow together, right? So, but think about this. You are using the most clever way. My question is, how long would this take? Will you use the dumb way? And the second question is, can you do better than log base to n? That is the question we need to ask in this. When you want to guess, how do you come up with a measurement? For example, you can come up with a measurement, right? If I want to guess the number from 1 to n, my measurement is actually I will ask log base to n. This is what we want to say in a whole semester. We call it big O and searching, big O algorithms, and we use it on searching. This is the diagram you're going to imprint in your mind to think about all this. I think we already mentioned we need to consider time in physics. We also talk about space, but in computer, so I think some people actually is very clever. They try to measure what is the light of speed, even is very, very fast. In computer science, we actually want to also measure the time and also measure the space. These two are both important and we'll mention, but we'll usually measure time more. However, time is not the exact time you want to measure. For example, what if you want to get a movie from Amazon? For example, the movie is about 14 gigabyte. You have two ways. One is you download it. One is you do a 2-day prime shipping. Which one you would prefer? Pirated? Okay. Let's don't talk about money and other factors. For example, some people like to collect the real physical disc. Some people like to save space, okay? But let's then just talk about this. My question is, which one is faster? Faster to get it. I mean, at this point, it's downloading, right? Probably downloading a movie will take you less than half an hour, okay? Wait a minute. What if I want more movies? Now I want the whole Marvel. I think it's not only 23 now, it's maybe 30 or something. If I want the whole set, is download faster or 2-day shipping faster? Well, if you're saying half an hour one movie, 23 movie may take you 12 hours, it's still faster than 2-day shipping. Still downloading win. What if you are one other movie? I don't know what is your favorite movie. Is it Lord of the Rings or is it some new animes or new DC, whatever? What if you want a lot of movies? Which way is faster? For example, if you download one movie that needs 8 hours, H can be 0.5, can be 0.1. What is the time you needed to download N movies? One movie needs 8 hours, 2 movies needs 2 hours. But how about shipping? Shipping takes 2 days or 3 days. No matter how many movies you take the same day. The time you needed to download a movie is H times N hours. N is the number of items, number of movies you download. So T is the time you download, TD, right? D means download, N means the number of movies. The time you need to download N movies is HN. No brainers, right? How about N movies when you ship it? No matter what, is 3 days. So the time for shipping, you say TS, S is for shipping, right? What do you think about these two functions when you plot the graph? This is downloading graph. This is this one. I'll get the pen out. Yeah. This is this one, okay? Downloading movies. Is this one, right? Linear progressions. Shipping is like that. What if you want to download all movie in the world? Okay, which one you prefer? Which one will win finally? If you want to download everyone, let's say you have the most fast internet, you only need 1 second in downloading one movies. You still need this, and the other one is constant. Will you choose downloading or shipping? Look at this graph. Before there's some time limit, when you talk about the transient state, which is here on the left, of course, you say, oh, downloading here is always faster. However, when you after this point of time here, what happens? Forever will be what? Forever downloading will be faster than delivery. No, sorry. The other way. Forever downloading will need more time than delivery. Is it? When your number of movie increase. So in our study of algorithm, we will actually usually do not care about the transient state. We don't care about this part. Let's erase it. Yeah, downloading faster, but it's for very small number of movies. What you care is on the right part here, this part. What if your volume of data item or movies are larger? That is the big trend. When N is large, forever downloading time of n movie will be larger than shipping time of n movies. Okay? So that is what we concern. When n is large enough, n is large enough, even your downloading time h is very small, no matter what, the downloading time will be faster. That is what we want to study in this one. Think about this. For these two algorithms, if you think that k is longer or k is larger, which one will go faster? Think about the left one. The left one, how many instruction of push do you do for k? If you think about this loop will loop 100 times. That means altogether, this function will do 100k. I don't know what k is, but on this one, you can see the two loops, k and k. That means this line will do k square push. Well, when k is equal to 10, what happened? If k is equal to 10, this one will do 1000 push. This one will do 100 push. Which one faster? Of course, you think, oh, this one is faster, right? Or not? Well, when k is small, definitely the right side is faster. But let's see. If k is equal to 0, k equal to 1, of course, the right side is faster. How about k is equal to 100 or 1000? You see, when k is equal to 100, they already meet the same point, which is a tie. But when k is more than 100, this is the left side slower, but this one already you change the sign. That means this one is slower. Okay, so we want to figure out what behavior of a crash of an algorithm will give you this forever so-called effect in the long run. For example, if I tell you there are three algorithms, the first algorithm, the time you need to do n items is this, like 100,000 millions. The second one is 100,000 n plus this 9999999. The third one is n squared. Which algorithm is the fastest in the long run? What do you think? 1, 2, or 3? In the very long run, when n is very large. But what one very big one? One is like that. Okay, you guys are right. The first one is the very is faster in the long run. Okay, let's try. For example, let's reduce the number a bit. Can you figure out this? When n is larger than 100, the second one will be slower. Because this become 1000 and added up will be larger than that one, right? When n is larger than 1000, the third one will be slowest, and so on. So when n is larger than 1004, the third one will also be slower than the second one. At the end of the day, conclusion you can say that is when n is larger than 1004, the time you need to spend on the third algorithm will be the longest, which is the slowest. So for this free timing, the coefficient, actually think about that, does not contribute much. What contribute more to the calculation? What do you think is the matter? Is it the coefficient or what? Power. The degree, right? The power is a degree of that. You can see that even if I simplify this into these three numbers, they are having the same order. That means T1 will be the fastest, T2 will be the second, and T3. So in order of whatever your T is, for example, like this is just anyhow I make up this function like that. Actually, we only take the highest power. So we use this big O notation to extract the power of the time for an algorithm. If Tn is equal to this one, 2n squared plus 9n plus 1. I don't know what is the algorithm, okay? I just anyhow, but I can calculate the timing is for that. I can conclude that this algorithm is On squared. So the naive way is, if you don't want to follow the real math definition, the naive way is you can just pick the highest degree or order and strip all the coefficient. This is how you convert to the big O notation. But of course, as a lecturer, I need to teach you what is the formal way. This is the formal definition. So the big O will actually put in here, right? This can be n squared, can be n, can be 1 whatsoever, right? So you want to change this. And this is your real time function. How should we design Fn? You will have exist a constant, two constant, n log, that means the minimal n and a c, such that here, your Tn will be less than or equal to c times that function. Sounds very abstract, right? Let me have some examples. For example, if my t is a constant function, let's say 1, 2, 3, 4, what does that mean? I want to satisfy this by finding what is this Fn. What is this? I can set Fn to 1 here. And then C is my 1, 2, 3, 4. And then you achieve this. Tn is equal to 1, 2, 3, 4. Forever you will be less than Fn times C. So I can directly say Fn equal to 1. Then that means that's why Tn is 01. Maybe you can see more clearly for the next one. What if my Tn is equal to this one? Okay. So what is C and what is n log? I can set C is equal to 4, 5, 3, which is this coefficient. So Tn is equal to 4, it's already here, okay? Tn is equal to this one, less than C is 4, 5, 3, this is C, right? And Fn is equal to n, right? Fn is equal to n. So Fn, which this one is equal to 4, 5, 3, n. Is that true? This one, is that true? It's true, right? Because 4, 5, 3, n minus 1, 2, 3 will definitely less than 4, 5, 3. And that's why this is correct. And I can say that this function is On. And how about highest power? Like this. So Tn is equal to 4n squared plus 24n plus 16. And this one will be smaller than this. Because this one is smaller than this. This one is smaller than this. This is the smaller side, smaller than that. And that means Tn will be smaller than 44n squared. And 44n squared, I can set C is equal to this, and n is equal to Fn is equal to this. That means I can conclude that Tn is equal to n squared, On squared. Okay. So this is a definition of how do you define the big O notation for a certain formula. So graphically, if this one is a Tn, okay, Tn means this one. The real timing function. And what do you mean by this one? This one, I means for any time, let's say this is your program execution. This is the orange line is how much time your program needs in order to finish the computation versus n. I can find a function Cfn that is bigger than that. That is the conclusion. then I can say that Tn is equal to OFN. Of course, this is not always the case because you actually Fn, sorry, this one is CFN. Wrong, CFN. CFN will be larger than Tn after here. Okay, so we don't care about this as a transient state. So after n log, CFN will be forever larger than this one. And that's why we can conclude here, Tn is equal to big On. I never change this typo. This will be CFN, okay? This one, I change the typo. So if Tn is equal to 1000 n, Fn can be equal to n, and I say Tn is equal to On squared. How about this? Can I say Fn is equal to n squared and Tn equal to On squared? Can I say that if Tn is equal to 1000 n? Can somebody say can or cannot? Very good, Benjamin. Can, but it's not, we call it not a tight bound. What does that mean? Your mom asks you, hey, how many marks can you get for your math? You said, oh, this year I do very well. My marks must be more than 0 mark. Is that correct? Yes, you can say that. But is that useful? No. So I don't know. That is for my case lah. I asked my wife, hey, we are going out already. How long can you get out of the house? My wife said, less than 1000 years. So it gives me a bound, but is the bound useful? Not really. So you can see that the same function here, you can give the bound as high as possible, but we call this one a tight bound. That means give you a useful minimal bound for the function. This one is not a tight bound, okay? Although it's correct, but in our course, I want to clarify that whenever I ask a question, if you ask me a big O function for certain function, I'm asking for the tight bound, okay? Don't give me this, you'll consider to be wrong. Although it's mathematically correct. Then of course, this one here, can I say Fn is equal to On? I cannot, because I cannot find the C and the N log such that whatever after that, the Tn is smaller than Cn. I cannot find that because Fn is equal to N. That's why Tn cannot be On. I can only say this function is equal to N squared and it's being bounded by N squared, okay? So that's how you do big O notation. Basically, there's some more rules for that. If a polynomial is degree k, you can simply say the big O notation is O to n to power k. And if you have two functions, let's say you have two algorithms, they are together, you want to add the time together. For example, the first part of your algorithm is n squared, 10n squared. The second part is 5n. Then you can conclude that after the first part, then the second part, this is your total time. Sorry. You can simply add the big O notation and it still will come to On. This is the addition rule. Multiplication rule or the composition rule, you can actually do the same thing. For example, there's a multiplication rule, there's a composition rule. And there are different way of doing this algorithm by you can actually have different way of so-called way to classify algorithms. We will learn all of this later, okay? For example, if it's constant time, that means no matter what, your algorithm will be the same timing. Log n time is just like just now our binary search. O n time is your linear search. And usually sorting algorithm is n log n. And you have other algorithm like that. Okay. Back to our movies. Some people actually, like, I think it's NASA, actually try to download 178 terabytes in 1 second. There was the network in NASA or UCL. Okay. And how do you know your algorithm in which class? That is all your thing you need to do in this course. You have a lot of algorithms, and this is where you are. You need to classify them into many different classes. That is the first thing in a class. Is it exponential, quadratic, whatever? This is what you need to do. And most of our questions in our exam and midterm will ask you this. So, but of course, we need to be more specific because nowadays we have many different type of algorithms. For example, sequential versus parallel, deterministic versus probability, or even biocomputer. Biocomputer is the algorithm you actually can use cells to compute. There's a very interesting algorithm, the computational model that people actually use solutions and cells and enzymes. For example, if they want to do two numbers addition, they will pour in some liquid, and this represents some types of numbers, and all the enzymes in the solution will compute what is the answer by their biological reaction, then will tell you the number. Okay. For example, sequential, we actually assume our computer is doing sequential. We'll do one instruction at a time, but you know that there's some GPU whatever can do many instructions at one time, and we'll assume the addition, the arithmetic operation is constant time, in which is not really true, but we'll try to neglect it. Okay. If you have an algorithm, you can count how many operations. For example, in this algorithm, you do this one assignment. The loops is k plus 1 comparison. And this one, I assume the addition is constant time. So there's k addition and this one. And a rough idea of this, you can actually analyze. This function will give you this 1 plus 1 plus k plus 1 plus 3k plus whatever. However, do you think all these coefficients actually does matter? Is it 5 or is it 4 matters? Not much, right? So actually, we don't actually need to know exactly how the numbers, because at the end, I can conclude this algorithm is okay, as k is the integer k. And if you have a loops, you need to loop k times lah. So usually we count it as OK time. If you have double loops, you have to multiply them. So for example, for this, how many times do I do this total plus is equal to total plus the integer? Is actually k square time. Okay. So of course, sequential, the first loop here takes k times, the second loop takes k times, and add them together, you still overall still k times. And of course, there will be a chance if you have if the else. Let's say if this one is O k square. This one is OK. Overall, what do you think is OK square or OK? I'm sorry that our algorithm people is a bit pessimistic. We actually only take the worst time. That's called the worst time complexity. Okay. How about recursive function? This is what we're going to do probably in week 4, week 5 lah. For example, anyone remember what is a Fibonacci number? I don't want to care about how we redo it, but Fibonacci number, if you talk about this, is 1 plus the number of Fibonacci that is computed n minus 1 and n minus 2. So very so-called naturally you have these formulas. And this step go to this step, you may need some mathematical derivation, but basically we'll say that Fibonacci number is O to power n. Okay. Of course, let's don't do this. Let's do some simpler things first. If you have an array, how do we use this big O notation to do searching? For example, the first one is linear search. Linear search means I don't have any idea where is the item in the array. There's no sorting. If I want to search an item 3, I need to go one by one. Is the first item 3? No. Is the second item 3? No. Is the third item 3? Yes. This is called linear search. You just search one by one. What is the time complexity of big O now if you have n items? You can say, I'm very lucky. When I search the first thing will be what I want. But I'm sorry to say that when we talk about time complexity, usually is the worst case. So the worst case, what is the worst case? The worst case is when your item is at the end of your array, or your item is not in your array. Then you have to go through all the items. Think about this. If I want to search if there is one person in Singapore named what? Taylor Swift. Of course, you know that Taylor Swift is not a Singaporean, but let's say you don't know. You want to go through all the Singaporeans to find if there's one person called Taylor Swift. What can you do? The only thing you can do is go through every Singaporean to see if their name is Taylor Swift. And at the end, you have to finish searching all Singaporean, which is a few millions, to find out that and conclude the answer. Oh, Taylor Swift is not a Singaporean. Okay, so the cost is ON. That's a worst case. But before we move on, what is the average case? This is an extra question. What is the average case? Very good. Lu Yu, right? The average case is n/2. How do you come up with that? Because you have different chances. I can search 2 times, I can search 3 times, I can search 5 times, I can search n-1 time. And if you want to find the average case, you sum up all the different number of times and divide it by n, in which it will n/2. But n/2 is O what? In big O notation, n/2 is what? Yeah, still ON, because you don't care about the coefficient. 1/2 is just the coefficient. So even the average case is still ON. However, of course, we can do better than that. What if you can do binary search? That means I can do divide and conquer. I can assume if I can have the array sorted, I can do this recursion. So all array on the left is smaller than me, all the right array is bigger than me. So if I do binary search, I can actually check the middle element. If the middle element is smaller than what I want, I can go to the right, and so on. If the middle element is bigger than what I want, I will go to the left. So it's basically the binary search, and you just repeat the search until either you find the items or you run out of item to find. Let's say I want to search for the key, the 25, and I look for the middle element, 34. Should I go left or right? And why? Of course, I first check if 34 is not the 25 I want to find, right? Now, should I go left or right to find? And what is the reason? The reason is because I know this number is 34. What will be the number on the right of 34? they will be all larger than 34. Will there be a chance that 25 is on the right? Any chance 25 can be on the right? Completely no. So that's why if I know that the item I want to search is smaller than 34, I can eliminate all the things that is larger. So I can narrow down to the left. And what do I do now? Recursion. I just do recursion to find this. That means I find the smaller one. Now 12 is not 25. Then 12 is smaller than 25. That means on the left of this, there's no chance 25 will be there. And I just repeat this algorithm. And what I can do is, after I repeat, I can narrow down, narrow down, narrow down. The white part is the narrow down thing until I find 25, then bingo. So this is the pseudocode for binary search. Each time I actually maintain the beginning of the array, the white part, and the end of the white part. I try to get a section between them. And each time I find the middle one here and go to search for that. Okay. For example, this beginning is the end. I search for the middle one, which is this one. And what I check is, oh, 34 is not 35. But if I do that, I can actually move my left and right hand to be concentrated on this white part. And now this is the middle, and I make the hand to like that, and until my hand actually either my middle one search for 75 or my left and right hand cross it. Okay. So okay, now what is the time complexity for this? What is the worst case? The worst case is when the key is not in the array, and every single line should be O1, right? How many loops are there? How can we argue how many loops are there? First of all, what is the exact number of loops? I think just now you guys answered already. What is the exact number of loops you need to do at most? First of all, you can see how many times you halve the array, right? When you do nothing, the array is n size. After one iteration, your array is n over 2 size. After 2 iterations, your array is n over 4 size, and so on. That means after d iteration, your array size is n over 2 to the power d. You will finish searching when the array size is equal to 1. So very simple question. When is the time n over d to power 2 to power d is equal to 1? Calculation, n over 2 to the power d equal to 1. That means n is equal to 2 to the power d. Log d put out, and that means d is equal to log n log base 2. And that's how we got the conclusion. The number of cuts is equal to log n. And that's how we conclude our algorithm is a log n solution. That's the complexity of our binary search. Okay. The same matter is log base 2, log base e, or log base 10. Do you think that matters? Why? Nigel, Gabriel, right? Very good. Not really. Why? Why it doesn't matter? Remember how the definition goes, right? The change of base is done, yeah, because, thank you, Ryan, right? Ryan explained that the change of the base actually can contribute to the coefficient C. So the coefficient C actually, whatever coefficient doesn't matter. It's just a multiplication of the coefficient C is still the same log. So it doesn't matter. Okay, very good. So that is actually a very good, brief introduction of Big O. Now let's have some application. I'm sorry to say that in this course, we have a lot of weird application and problem you have to solve. This is not a very weird problem. It's a useful problem. See whether you can solve it. Assume no two elements are the same in an array. How do you find the global maximum? And your array is not sorted, okay? Or actually later I'll talk about whether the array is sorted or not. And what is the complexity? It's easy. If you want to find in an array what is the global maximum, which means what is the largest number in the array, I'm sorry to say that you have to scan through the whole array to check which one is larger. However, usually we don't do that. Instead of the last problem, this is called a global maximum. Sometimes we find a local maximum. What is local maximum? Local maximum means I want to find an item in my array such that the left side and the right side are smaller than it. Okay? For example, in here, 9 is so-called the local maximum because 4 and 2 is smaller than it. How about, can you find another local maximum in this array? Thank you, Sanjay. The other local maximum is 11, 23, and 17 because the number beside him are smaller. And you ask what is it, they're the same whatsoever. So I think that's why we have this assumption. No two elements are the same, okay? Okay, this is called peak finding. You always have some function. For example, this actually you can talk about the array is the result of a function. Usually you can find a global maximum. This is actually not an imaginary problem. A lot of computation problem is given you a function. You want to find what is the global maximum. It's very simple. No matter you're in fintech, finance, whatever, you actually have to do that. Because finding a global maximum is the perfect ideal situation, but sometimes you don't need that. Sometimes you just want to find some local maximum. Why? Global maximum usually is the perfect solution for your problem. For example, if you are using in a power plant, if a lot of constraint, you can actually find the solution that is causing you the less in energy, money, whatsoever. However, it's hard to find. Local maximum usually is faster to find, and sometimes is a good enough solution. So, how do you find the global maximum in an array? If your array is unsorted, I'm sorry, you have to go through the whole array, and that means your time complexity is O(n). It depends on how large your array is. Of course, if you're lucky you have a sorted array, then you know where is the maximum is at. It's either on the left side or on the right side. It's constant. But of course, if people already give you a sorted array, it's like a no-brainer problem. How about local maximum? How can we find a local maximum? Anyone. I just need anyone. Do we need O(n) time to find a local maximum? Remember, the local maximum means any number that is larger than its neighbors. Okay? Can we do binary search? Okay, the normal binary search is I want to find the middle element. And if I find the middle element, I can check if it's a local or local maximum. If it's local maximum, I finished already. So the very simple question, what if it's not? For example, this 6 is not. Where should we find? Ryan suggests we find the slope. Correct. We can find the slope. Okay, now, if the number is not a local maximum, what does that mean? It means either one of the following case. Left is smaller, right is smaller. Then too bad it's not, because it's actually the local maximum. We finished already, right? The other case is left is smaller, right is bigger. Or the other case, in which the first case is ruled out. Because if the first case is the local maximum, your algorithm stop. How do we continue? So we suggest we do recursion, but recursion on the left side, on the right side, and why? So do you think we should recurse to the smaller side? Because you see this one, right? One side will be smallest. Smaller, bigger, 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 smaller. Okay. Can we go to the smaller side? First, the obvious problem is what if both sides are bigger? You don't have a smaller side. Will there be a peak in the smaller side? The answer is what if it's monotonic decreasing? Then you don't have a peak. So if you go to the small side, there's a chance that you cannot find a peak there. So we don't go for the small side. But the other question is, how do you guarantee there's a peak in the bigger side? If you want to go to the bigger side, will there be a peak? What is the worst case? The worst case is what if your number is monotonic increasing? If monotonic increasing, will there be a peak? Where's the peak? If it's monotonic increasing, the last one is the peak. Why? Because the peak says nobody on my left side and the right side are bigger than me. Then if you go up all the way, the last one will be the peak already. So that means on the bigger side, you always will have a peak. Graphically, it's like that. Let's say this is your midpoint. One side is smaller, one side is bigger. The left side, the left side, you go all the way down. That has no peak here. But the right side, you may have a peak there, like this is a local peak. But even if you don't have the local peak, you have to come to the end. And the end point is actually the local peak because the end point is bigger than its left side, and the right side have nothing. We can deem it as the right side is like all the way to down, negative infinity. So you can treat the last one as a peak. So very simple. I can do so-called binary search. So very simple. I check the middle one. The algorithm is if it's a peak, finish. Otherwise, I recurse into the bigger part. Then I continue the algorithm until I find a peak. And I will and I must find a peak. And now, if it's a recursive algorithm like a binary search, you tell me what is the time complexity right now. Simple question. What will be the time complexity? Binary search, right? That means is O log n. Okay, now, if you are ready, let's go to 2D. How about if I have a 2D array, I want to find a local peak. A local peak means I just need to find if the vertical array, my number is bigger than my north and south neighbor, and also in a horizontal array, my number is larger than my east and west neighbor. I will satisfy as a local peak. Okay? How would I find it? Well, let's see. The first algorithm I try is I find the global maximum for each vertical column. For example, here I find the 7953, and here, then I will find, will it works? What is the time complexity? Will it works? For example, this time I find 9, right? 9 is the global maximum, and now I find the local peak on my gray area. The output will be larger than its vertical neighbor, and the output will be larger than this horizontal neighbor. So this algorithm actually works. But what is the time complexity? I'm sorry to say that to find each of the gray global maximum, you need O(n) time for each column. Then for m columns, you need to repeat it m times. So too bad. Even though you have m columns, you only need log m time for our last clever algorithm. Your overall algorithm is still OMN plus log m. So if you want to do n over that, or n is like m, you still need n square algorithms. Slow. What if instead of global, each time in the gray area, I find the local maximum? Does it work? I'm sorry to say that it doesn't work. For example, this example already show you it doesn't work. 4 is the local maximum for its column, but after you find that, it becomes the local maximum of this horizontal area. But if you check this, 4 has a bigger neighbor of 5. It doesn't work. Too bad. Are we stuck? Are we stuck with NM? Let me introduce you a clever algorithms. What if we still want to find the global maximum by not finding the global maximum? Am I saying some nonsense? Let's see. Can we try to find this local peak of all the global maximum by not finding this global maximum? The clever tricks here is, how do I find this without computing all the global maximum? I skip step 1, I do step 2, but I have no number to do in step 2. But I can do the following things. I can do lazy evaluation. That means if I need that, I compute that. What does that mean? This is called lazy evaluation. I just want to be lazy. But lazy doesn't mean I do nothing. I will only do the things on demand. For example, this gray part is all the global maximum I need to compute for each column. But I don't compute them. But now I want to do the local maximum to find if this one is a local maximum. If I need to find if this is a local maximum, I need the 3 numbers in there. So at this point, I compute the global maximum of these 3 by scanning the whole vertical column of these 3 columns only. Then I know the numbers. And now I know that 10 is a peak or not a peak. It's not a peak. Then I recurse to the right. When I recurse to the right, I'm supposed to find this. And at that moment, I will do lazy evaluation to compute the columns. Then I only compute all these 9, 10, 12, 18, whatever number when I need them in my local peak maximum computation. So will it be better? I use the 1D peak finding algorithm that is log n. The running time is log m or log m, but each time I compute each column is log n. How many columns do I need? Actually, I need to find log m times, and each time I need to find 3 columns, right? And that means it's 3 times log m times log n times n. That means ultimately my algorithm is still log nm, which is a lot better than n times m. Okay, so that is how we improve. And I'm sorry to tell you that in our course, we always need to do this type of things. Improve and find an algorithm that is a lot better than brute force or extensive searching. Okay. Okay, lastly, before we end, we are talking about big O notation is about the worst case. That means when you think about this, that means my algorithm's worst case is being bounded by a ceiling. That is something good. That means you say, oh, it's like budget planning, right? Let's say my project will spend at most $1 million. That's how you plan. But sometimes some algorithm or something will have the reverse question. What is your best case? That means your worst case is a function on top that bounds your real timing here. Sometimes you have to describe the other way. That means I want to find a functions that say, oh, whatever your time, your space, has to be at least this one. So this is called the lower bound. The worst case, go back to that, is actually called the upper bound. For the lower bound, we'll use the omega function. But then, basically, your definition is the same, except because it's lower bound, that means my function has to be less than your time being. And ultimately, if somehow your lower bound function and your upper bound function, reverse, your upper bound function and your lower bound function, if the same function, we can say that is theta. Theta is like that. After a certain time here, your C1 times the function and your C2 times function is sandwiching your time all the time from now on. Then if it happens like that, I will call that your function is theta, theta Fn. So you can verify this. Your theta with, for example, if it's linear function, it's a theta n function. N cube function, you cannot say it's theta n square function. Okay. Okay, so that's it for now. I will try to see whether you guys understand by this small quiz. But I think I will leave the quiz next time, maybe. Oh, let's try. Let's try to do the quiz now. Okay. So if you are still here, can you do this? Please help me to scan this. Can you see this? I also put the link in the chat. Can you log in this and see whether you can see, can join this? Okay. Scan this or click the one in my chat. Play, right? Play. Yeah. Okay. Ready? Need more time? Okay, let's see how many people are there. What is the big notation, big O notation for this function? Okay. Okay. Good job. Most of you got it. The highest function is n to the power 4, so it's a n4 function. Next one. Good job, good job, good job. What is the big notation for this one? This one is 4 to 4n squared log n. Okay. Good job. This is n squared log n. So n squared is not actually accurate. O n over 3, yeah, is correct, but it's not the tightest one. So if I ask you the tightest one, should be this one. So theoretically, n to the power 3 is correct. You can say that this is actually big O n to the power 3, but I will ask you the tightest one, which is this one is the correct answer. Okay. Okay, what is the best big notation for this one? N da 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 da. Why? Why the second option is better? The second option is the correct one, and most of you got it wrong. Why? Because log n squared is 2 log n. And we don't care about the coefficient. So the correct answer is actually n log n. Okay? Learn this out. Now the good thing is you have this here. If I put it in the midterm or quiz, then you will get this right. Okay? Okay. If the running time to insert an item is the head of the linked list, depending on how many numbers in the linked list, if there's n items in the linked list already, good. Inserting an item in the linked list, you just need to insert the head. You don't need to go through. Even though you have 1 million item in the linked list already, it's still constant time. That's why the stack is fast. Okay. What's the running time of searching for an item in our linked list? So far, the implementation so far. Linked list. Good job. I'm sorry, the linked list is not sorted, so you cannot do binary search in the linked list. That's why you can only do ON searching. Okay. Finally, who is guest 27267? Okay. Congratulations. Maybe next time I should set some prizes for this. Okay. But I hope you guys can get over the solution for that, because I think that's quite important. And those questions will be in the midterm and quiz, and not midterm, we don't have midterm, sorry. In our quizzes and also in our final exam. Okay. Any more questions before we end? If you have, please, I will use 1 minute only. If you have question, please press your whole hand questions in your reaction. Otherwise, within 1 minute, I will stop this recording. Thank you, Ryan. You're good, and there's a few good ones here giving me response, and we really thank you for that. Thank you, and happy Chinese New Year. Yes, just to share this again. Happy Chinese New Year. The most important is line not so easy. Day no bug. Yeah. Okay, I can explain the n log square n again. Okay. This one. N log n. Oh, sorry. Can you see that? This one. N log n. This one. This is, sorry, your school math. N log. Very hard. 8 n square plus 4n. Okay. First of all, this one can simplify it be n log 8n square. Okay. So coefficient doesn't matter. This finally become n log n square. And now what is log n square? If you remember your math, log n square is equal to 2 log n. And put this n back is n times 2 log n. And that's why become 2n log n. And 2 log n, we don't care about the coefficient. That's why it's n log n. So that's it. Okay, I hope it clear out. Yeah. Any more questions? No, then happy Chinese New Year. Remember, get more 红包, ang bao, whatever it is. Okay? Yeah. Thank you. See you.
Sorry,
Bye-bye.
Prof, can I ask?
Yes. Let me
Can